Okay, hello everyone. I'm Jianjun from Icon team, and my work is focusing on the device model development and optimization. I'm also working on the Windows as a guest on Icon. Today, I will give an introduction about the shared memory-based Inter VM communication in Icon. This is the agenda. First, we will talk about the shared memory-based Inter VM communication overview. It will cover the Ivse memory spec in the open source community and the Icon's Ivse memory design philosophy. Then we will talk about the DM land and hypervisor land implementation of the virtual device in Icon. Finally, we will talk about how to enable the Ivse memory device in Icon and how to use UIO to communicate with the device. If you have any question, please stop me. This is about the overview of the Ivse memory spec. Actually, Ivse memory spec is defined by the open source community, and the Ivse memory device is emulated as a PCI device, and the shared memory is exposed to the guest VM as a PCI bar. And the shared memory is allocated from the host side or the hypervisor side. In KVM, it is allocated from host. And in Icon, we also supported that hypervisor land Inter VM. So the shared memory can also be allocated from hypervisor. And the spec defined two kinds of device. The first one is called Ivse plane, which only support the shared memory. And the second is called Ivse memory doorbell. It supports the shared memory and also interrupt it supported. It is called doorbell mode. And we will discuss how to implement this in Icon later. In the guest VM, we use different driver to access the device. On Linux side, in Linux guest, we will use the UIO framework to propose the device, and the UIO framework will expose some physical resources to the user space application. And on Windows side, in the open source community, there is a dedicated Ivse memory driver. It can be used on Windows side. It is something like the character device driver in Linux, and the user application can open that device. Then it can use I/O controller to communicate with the device. And this is about the bar. This is about the bar definition in the Ivse spec. The bar 0 is for the reject. Currently, there are 4 rejects defined in the bar 0. Offset 00 is and 04 are used for the legacy interrupt, which is only valid for the revision 0, in which only legacy interrupt is supported. And in Icon, the Ivse memory follow the version 1, which means the first 2 rejects are not supported and are not used in the Icon Ivse memory emulation. The third and the 4 rejects are implemented in Icon. The offset 08 is a read-only reject. It is used to identify the device ID. As you know, if more than one VM try to communicate through the shared memory device, each side must has a unique ID. This one is used for that. And the offset 0C is a write-only register. It is used to trigger an interrupt to the peer side. And the bits 0 to 15 are used for the vector number. And the bits 16 to 31 are for the target. For example, currently more than one vector can be supported by one Ivse memory device. So you can use the bit 0 to 15 to specify the vector number. And you can use the bit 16 to 31 to specify which peer you are going to trigger the interrupt to. And the bar 1 is for the interrupt MSIX bar. This is the normal PCI bar. And the bar 2 are used for the shared memory. It is a MMIO bar, and the allocated memory are mapped through EPT to the guest VM. So this is about the bar layout. They are all defined by the Ivse memory spec. Now we will go to the design philosophy in ICON. ICON Ivse memory device emulation followed the Ivse memory V1 spec. So the Inter VM communication are compatible between the KVM and the ICON, which means if Inter VM communication are developed or are working on the KVM, they can be used on ICON guest VM. We don't need to change anything. And also, on the other side, the existing Linux driver and the Windows driver can be reused. And on the other hand, ICON will stick to the development direction of KVM community and involve accordingly. So this is about the shared memory virtual device design philosophy in ICON. We follow the open source community spec. This is regarding the DMNAND Ivse memory architecture in ICON. You can see that a virtual device is emulated in the ICON DM, and the shared memory is allocated from the SOS. It is through the Linux shared memory interface. On the Linux side, which means the left block, UIO driver is used to export the device resource to the user space. User space application operates on this resource, such as registers and the MMIO bar. They can use them to communicate with the device. And on the right block is for the Windows. On Windows side, we have a dedicated Windows driver. User space application can use I/O control to communicate with this driver. So the data, the communication between the different guest VM can communicate with each other. In ICON, we also implement the hypervisor LAN Ivse memory virtual device, because ICON we need to support the pre-launched VM. For pre-launched VM, there is no device model, so we must implement another virtual device in hypervisor itself. In this solution, the drivers and the user application in guest VM are the same as those with DMLand implementation, which means DMLand or hypervisor-land IVS memory implementation is transparent to guest VM. In hypervisor-land IVS memory, the virtual device is emulated in the hypervisor itself, and icon config tool is used to enable and configure the IVS memory device in hypervisor. Hypervisor-land IVS memory can use to communicate between the pre-launched VM and the post-launched VM. So for pre-launched VM, the virtual BDF and the virtual bar are allocated by the config tool, and for the post-launched VM, the resource such as BDF and the vbar address space are allocated by the device model, which is the same as DMLand. But if the IVSH virtual device is emulated in the hypervisor, the device model must use hypercore to convey this information to the hypervisor, which means the virtual BDF and the virtual bar address. This must be conveyed to the hypervisor through hypercore. For hypervisor-land IVS memory device, the hypervisor must reserve a memory pool which is used by the virtual device. This memory pool is configured by the config tool, and they are reserved and managed by the hypervisor. So the hypervisor will manage this pool and assign a buffer to a virtual device according to the configuration. So we just talk about two kinds of implementation for the IVS memory device in ICON. In these slides, we will compare them, and the DMLand IVSH memory device is emulated in the ICON device model, and the shared memory region are reserved in the service VM's memory space. This solution can only support the communication between post-launch VM. If we want to communicate with pre-launched VM, we must use hypervisor-land IVS memory solution. The hypervisor-land IVS memory device is emulated in the hypervisor, and the shared memory region are reserved in the hypervisor's memory space. Please note that if you want to communicate between two VM, these two VM must use the same solution, which means if one VM is used DMLand, the peer side must also use DMLand. We cannot combine the DMLand and the hypervisor-land solution in the same channel, I mean. So this picture combines the DMLand and hypervisor-land implementation in ICON in one picture. This picture emphasizes that if we want to in the currently ICON mainline, the doorbell mode is only supported by the hypervisor land, the Inter VM, and the DMLand only supports poly mode, which means the doorbell mode is not supported. That is why, that because the blue module, I mean the Ivse memory server, is not implemented yet, and the plan is maybe 2.5 or 2.6. This module will be implemented. So by then, the DMLand Ivse memory device can also support doorbell mode. So currently, only if you want to enable doorbell mode, you must use the hypervisor land solution. The Inter VM server is a dedicated process which is used to communicate between different ACRN DM process. It's used to forward the interrupt request from one to the other. So if one gets the VM trigger the doorbell, the other side, which means the other gets the VM, can receive that interrupt. And this module is not implemented yet. So we will go to the UIO. As I mentioned before, on Linux side, we are using the UIO framework as the driver for the Inter VM virtual device. The UIO is used to expose the physical resource of a device to user space. User space application then can map the bar to its virtual address space, and so a user space driver can be implemented. When a UIO driver is probed on a shared memory device, some sysfs nodes will be populated, and the application can use them to retrieve the physical resource information. So they can use them to write regex to trigger an interrupt. So this, of course, we can implement a dedicated Linux driver for the shared memory device. This is about something we need to highlight about the hypervisor land Inter VM in solution. For hypervisor land Inter VM implementation, the shared memory is reserved by hypervisor and is configured by the config tool. And this shared memory cannot be claimed by the system. And this shared memory size is fixed. It is determined by at the build time. The ownership of the origin also are determined by at the build time. It is not possible to change them at the runtime. So this is the philosophy on ICON. All the resources are fixed at the build time. The resources are static. You can use config tool to configure them. So finally, we will go to the Ivse memory usage, how to enable them, how to use them. For the DMLand shared memory device, it is easy. We only need to add an embedded device in the ICON DM command line. For example, the yellow part. You need to specify a PCI slot, and you also need to specify the shared memory name. This is used to pair this is used to specify how many VM are using the same the same shared memory. So if two guests the memory are try to communicate with each other, they must use the same name here. And about the shared memory size, please note that it is in megabytes, and the range is for 2 megabytes to 1512 megabytes. This is about the how to enable the shared memory device in for DM LAN. It is easy, and for the hypervisor LAN shared memory device, first we must use config tool to enable, and we also need to configure the shared memory name, how many the shared memory size, and which VM are going to use this shared memory to communicate with each other. So you can use config tool to enable them and configure such kind of information. And these parameters are almost the same as DMLAN, but you need to specify the VM ID. In icon, the VM ID is also configured by the config tool, so you can specify them in unconfig also for the shared memory device. If you have configured the shared memory correctly by icon config tool, you can check the generated XML file to make sure it is enabled. And for this is about how to check whether the Ivse memory device is working on Linux side. If you have enabled them in the command line, you can check by ASPCI in the guest VM. And when before your application can communicate with each other, you must probe the UIO driver and the UIO PCI driver, and bind this shared memory device to that driver. Later, you can use the sysfs node populated by the UI driver, and your user application can use them to communicate with each other. So that's all for my topic. Do you have any question? Jeffrey?
Thank you.
Yes, I'm just interested how one virtual machine can generate MSIX interrupt to another virtual machine. Is it possible? It's strange. I see MSIX resources for shared memory. How it could be used?
When UIO driver is probed, all the physical resources are exposed to the user space. In this slide, there is a register. So this bar can be mapped to the user space application, and the user application can only need to write write a D word to this 0C register. For example, if VM1 need to trigger a interrupt to VM2, you can specify the bit 16 to 31 to as 2, and currently 8 vectors are supported by one virtual device. So you can specify such as 0 to 7 in the bit 0 to 15, and when the guest VM write to this register, a VM exit will happen, and the hypervisor will emulate that by trigger an interrupt to the peer side. That is how the interrupt is forged to the peer virtual machine.
Yes, thank you. So in this case, communication between virtual machines can be very fast. Thank you.
You're welcome.
Any more question on this?
I just have an additional question to the performance of this mechanism, mainly regarding the interrupts. Do you have any numbers how long it takes to transition the interrupt from one machine to another?
We have internal tests about the latency.
Yeah.
Generally speaking, as you know, the communication just involve memory copy, and the max latency result from the task switch in the user VM. I mean the memory read write is very fast, but if you are running as a user-based application, the user application will be scheduled by the guest OS. So if the user application is not scheduled in time, it will introduce additional latency. The memory read write is very fast, and yeah.
Okay, thanks.
You're welcome.
One question, Jianjun Vinay here. I understand the HVLAN is used to allocate the shared memory between a pre-launch and the post-launch, right?
Yeah,
so,
correct.
The hypervisor will allocate this memory. Can I use the same HVLAN between two post-launch, like the Windows?
Yeah, of course.
And
yeah, of
okay.
course, yeah.
Okay. Because in this case, I know the hypervisor allocates the memory, and it's not the Acon DM.
Yeah,
okay,
yeah,
thank
correct.
you.
Yeah, you're welcome.
Thank you.
There's the next question on the chat. Do we support Ivse network device?
Yeah, that's a good question. Yeah. Of course, we can implement a network driver based on the shared memory device. This is possible. And by this we can use the socket interface for the user application for the user space application development. This is very good, very friendly for the developer. Yeah, this is a good question. But currently, the driver, I mean the network over shared memory, is not ready. We have plan for that.
We have plan, or we don't have plan for that?
We have plan.
Okay. Very good. Any more questions? No? Okay.